significant, it's so large that it has the ability that if anything passes near Jupiter, one of two things is going to happen. It's either going to get sucked in by Jupiter, or it's going to get slingshotted in a completely different direction. And Jupiter is big enough to do that to Earth-sized planets. And so my point is we interact with each other, and not directly. We do so via gravity for the most part, but we do, and we are susceptible to changes throughout the entire solar system. They affect everybody, and Earth included. So we recently discovered that the moon spins just like Earth does. The reason that you see the same side of the moon, when you look up in the night sky and you look at the moon, it's the same face every single time. And the reason for that is that the moon rotates on its axis just like the Earth does. But the amount of time that it takes the moon to go around the Earth is a little over 29 days. It's like 29 3/4 days. Well, that is how fast or how slow the moon is rotating on its axis. So it always points in the same direction towards Earth. We have recently discovered that the moon has begun wobbling. And think of it this way: a child's top is spinning on the kitchen table, and it's beginning to lose a little bit of energy, so it wobbles. Well, that's what the moon is doing right now. And it's going to have an impact on tides here on the surface of Earth. You're going to see areas that are going to experience much higher tides than they're used to, and other areas are going to experience no tides that normally would have tides. And so something as, you would never, so big deal. What's the big deal? The moon's wobbling. Yeah. Well, Earth feels it. And the same thing's true, we know, with anything else in the solar system. Earth feels the effects of it eventually. And the other planets go through the same thing. I mean, we're not alone in this. Everybody interacts with everybody. Most of the time it's via gravity. And the moon's wobbling is altering the gravity forces between us and the moon, and it's going to alter the tides on this planet. Okay, I think everybody is here. Let me get started.
Recording in progress.
All right, there were a couple of questions about the exam last week, so I'm going to go over the answers to exam 2 here real quick, okay? I know some of you might have questions about it. I'd like to keep that part of this pretty brief if we could, okay? So if you have what you think might be a long question, let's wait until after I finish and then I'll help you with it, okay? But anyway, beginning with question number 1, nitrogen, the most abundant gas. Number 2, along with solar energy, you need CO2 or carbon dioxide. Concentrated over the polar region was ozone, or O3. For CO2 is greenhouse gas. And number 5, the blue color of the atmosphere is due to the presence of nitrogen in our atmosphere, okay? Question 6, this is the multiple choice. The correct answer was A. 7 was C. 8 was A. 9 was C. 10 was B as in boy. 11 was D as in dog. 12 was E. 13 was B as in boy. 14, D as in dog. 15 was B as in boy. 16 and 17 were D as in dog. 18 was B as in boy. 19 was C. Okay, this was the matching part on that blank diagram that I provided you. So beginning with number 20, the letters are F, H, D as in dog. 23, I was looking for G, but I accepted the letter E. So 23 would be either E or G. 24 is B as in boy. 25 is A. 26 is B as in boy. 27 is H. 29 is F. 29, I accepted either E or G. And 30 was D as in dog. Now the true false. 31, 32, and 33 were false. 34, 35, 36, and 37 were true. Nobody got 38 wrong. 39 is false. 40 is true. 41 is false. 42, 43, and 44 are true. Nobody got 45 wrong. 46, 47, and 48 are false. And 49 and 50 are true.
Can you repeat 29?
I accepted either the letters E or G.
Thank you.
Mm-hmm. I know some of you had a bit of anxiety over this. Overall, you did pretty good on it as a class. And don't be too terribly hard on yourself regarding this material. Keep in mind, teaching in this fashion, it takes an effort on your part as well, and I understand that. And this is material. It's not that you have an inability to understand it. You do. It's just it's brand new to you. That's all. That's all it is. And some students are here in this class are returning students. They're relatively new, maybe 1 or 2 semesters, and that's it. Or maybe this might even be their first semester. Keep in mind that in the early part of your education, when you attempt to do the best that you can in a particular class, you're going to do so by a technique which you're completely unaware of. You're going to practice what's called rote memorization. You're just going to memorize factoids. That's all you're going to do to pass the test. And in the early days, like the very first semester, when you're taking those basic classes, that might potentially work. But at some point in your education, you're going to have to break away from that mode of thinking, and you're going to have to really work toward understanding the material and grasping it and understanding the concepts that are trying to be taught. And because just memorizing factoids won't get you through to your senior year, you're going to struggle a lot more and more if you do that. So don't be hard on yourselves over this exam. This was new material, a lot of new vocabulary and new concepts. You gave it your best shot. Many of you did very well on it, okay? So just keep that in mind. This practice of critical thinking, which is what I'm advocating of critical thinking, it doesn't involve rote memorization. This critical thinking, you can take it into any class that you take. This geography class, a math class, a English class, doesn't make any difference. Question everything. Don't be afraid to ask questions. Don't be afraid to speak up. And that's how you begin the process of critical thinking. Okay. All right. That being said, any real quick questions so far before I get started on the study guide for exam 3? Okay. Study guide for exam 3. The first section here talks about atomic structure, protons and electrons. Now, in one of the PDF files I sent you, there are diagrams there. Now, as a reminder to you, everybody, no, I'm not going to ask you to solve any chemistry problems on this exam, nor am I going to ask you to, combine atoms or anything like that. I'm merely giving you this section of material as explanatory material, informative material. There's only 2 small portions of information that I want you to know for the exam, and I will point those out to you when I get to them, okay? So I'm about to explain atoms here to you. Don't be stressed out over this. I'm not going to ask you any questions on this particular topic, okay? So you already know there's 92 naturally occurring elements inside the Earth. The vast majority of them are found in trace quantities. Only about 8 of those 92 elements are in any significant quantity. Okay, and so that means the remaining 84 elements are in trace amounts. Okay, and now elements combine to form compounds, which eventually develops into a mineral. Okay, and so the example that I gave you yesterday, the 2 single most common elements inside the Earth are silicon and oxygen. When you combine those 2, you create a mineral that we call quartz. Okay, quartz is nothing more than silicon oxide. It combined to form a mineral, quartz. And so in this section of material, why do some elements combine and others don't? What's the big deal here? So there are 3 basic parts to every atom, no matter what the element is. Every single atom has 3 basic parts to it. 2 of them are called protons and neutrons, and they are located in the nucleus of every atom. Surrounding the nucleus is the 3rd part. surrounding the nucleus and going around the nucleus in an orbit, these are called electrons. No matter what the element is, the atoms that make up that element all share those three basic parts. The difference between all of the elements on the chemical periodic table is the combination of these elements, the configuration of them. It's like a jigsaw puzzle, everybody. You got the same pieces, but you can make 92 different pictures out of these puzzle pieces. Okay? So for instance, if you were to look on the chemical periodic table that I provided you, everybody, element number 1 is hydrogen. What that means is there's one proton in the nucleus, and there's one neutron in the nucleus, and there's one electron going around it. Here's what I want you to know for exam 1, everybody. The number of protons in the nucleus identify the element. So for example, element number 1 is hydrogen. Why? Because it only has one proton in the nucleus. If you were to tell me that there were 26 protons in the nucleus, you could only be speaking about iron. Iron has 26 protons in the nucleus, and it is element number 26 on the chemical periodic table. If you tell me there's 10 protons in the nucleus, you can only be meaning neon. If you tell me there's 18, that has to be potassium. So that's how that works. The number of protons in the nucleus identify the element. From this point forward in my explanation, everybody, I am going to completely neglect mentioning neutrons from this point forward. All I'm going to talk about are protons and electrons. Protons are in the nucleus, and they have associated with them a positive electrical charge. The electron that goes around it has a negative electrical charge. And if you remember as a child playing with magnets, you knew that if you pointed the magnets toward each other, if the two magnets were aligned properly, they would stick together. But if you turned one of the magnets around, they would have a tendency to want to push away from each other. Well, if you have opposite charges, a positive and a negative, they are going to want to attract to each other. They want to cancel each other out. And this is, you might say, the glue that holds reality together, because it's the electromagnetic relationship between the positive protons and negative electrons. It's holding the atom together. Now, as you get up into bigger and bigger elements, say, let's let's start not too terribly big. Let's start with something like sodium, everybody. As an example, sodium is number 11 on the chemical periodic table. That means it has 11 protons in the nucleus. It also means that it has 11 negatively charged electrons going around it. If you look at the diagrams that I provided you, everybody, in the case of sodium or any other element, all of the electrons do not go around the center of the atom in the same orbit. They look like they're spread out. And there's a rhyme and a reason to how they are spread out. Each of those little circles around the nucleus is an orbit. We have discovered that each of those orbits, the one that is closest to the center, is referred to as orbit number 1. And then as you move outward, it's orbit number 2, then 3, then 4, then 5. So there is a easy formula to determine how many electrons each orbit can carry. So the formula is nothing more than 2n squared. That's it. N is the number of the orbit. So for instance, orbit number 1, substitute the letter N for 1. 1 squared is 1 times 2 equals 2. So that means the very first orbit can hold a maximum of 2 electrons. Orbit number 2, substitute number 2 for the letter N. 2 squared is 4 times 2 is 8. So orbit number 2 is capable of holding 8. Now, a reminder, everybody, I'm talking about sodium here. We have 11 protons in the nucleus. We've already shown there's 2 electrons in the first orbit and 8 electrons in the second orbit. That's only 10 electrons. There's 1 more to go. The third orbit is capable. 3 squared is 9 times 2 is 18. The third orbit is capable of holding 18. However, sodium only has 1 more electron. Now it will go into the third orbit. There's no rule that says the orbit has to have 18. It just can't have any more than 18. It can have less, but it can't have more. So you have 1. Now the electron configuration of sodium. Remember 2 in the first orbit, 8 in the second, and 1 in the third orbit. So you've got the numbers 2, 8, 1. That is sodium's electron configuration. And here's the second piece of information I want you to know for exam 3. The electron, excuse me, the electron configuration of any element determines that element's chemical and physical properties. The electron configuration determines that element's physical and chemical properties. What do I mean by physical and chemical properties? Well, what color is it? What is its boiling point? What's its boiling temperature? What is its density? How heavy is it? How easily does it mix with other elements? These are the chemical and physical properties I am talking about, and they are dependent on that electron configuration. Now, every element has a different electron configuration. Sodium's just happens to be 281. So far, the only thing I need you to know for exam 3 is number 1, the number of protons in the nucleus identify the element. Number 2, the electron configuration gives that element its unique chemical and physical properties. The rest of this is explanatory for you, okay? I'm explaining those diagrams to you that show you elements that are being combined. Something I haven't explained to you yet, and as much as I spoke about critical thinking earlier today, I'm merely going to gloss over this particular topic because it's not really that important that I get into the details about why this is. You just need to know to understand my explanation, everybody. No matter what the element is, no matter what its electron configuration is, the outermost orbit, the electrons that make up the outermost orbit, are commonly referred to as valence electrons. Valence is spelled V-A-L-E-N-C-E, valence electrons. That merely means the outermost electrons. When two elements want to combine with each other, they are going to interact with each other through their valence electrons. They are not going to join nucleuses together. Because if you think about this, everybody, if you take, say, element sodium, which is number 11, and let's just say you wanted to combine it with oxygen, which is number 8, no, you wouldn't end up 11 protons in the sodium nucleus, 8 protons in the oxygen. No, you're not going to slam these two elements together and get 19 protons in the nucleus, because if you do that, you're going to get a big kaboom. And 2, you now have 19 protons in the nucleus. It's not sodium and it's not oxygen anymore. 19 happens to be potassium. So no, they are not going to join in that fashion. How they are going to join with each other is through their valence electrons. And I'm going to give you a real quick, easy example of how that works. I've already explained hydrogen to you. It's got 1 proton in the nucleus, 1 electron surrounding it. Here's what I haven't told you yet. I gave you the formula to figure out the number of electrons in each given orbit. So orbit number 1, the answer was 2. Number 2, the answer was 8. Orbit number 3, the answer was 18. And if you go up to orbit number 4, 4 squared is 16. And then times 2 means orbit number 4 can hold up to 32 electrons. Okay. Elements are considered stable when they do not change. Some elements naturally change into something else. And so that means they're unstable because they're changing. If the element cannot satisfy the 2n² formula in its outermost orbit, and in the case of sodium, number 3 was capable of holding 18, yet there's only 1 in that orbit. So let's put it very simply here, everybody. In order for sodium to be totally happy, it would like to have 17 more electrons in that orbit. It would like to, make it an even 18. But if it loses one, if it loses that 1 electron that happens to be in the 3rd orbit, doesn't that now make the 2nd orbit the outermost orbit? And has it not satisfied the 2n² formula? Yes. So sodium is going to want to naturally lose that outermost electron. And when it does, you still have 11 positively charged protons in the nucleus. However, they are now surrounded not by 11, but by 10 negatively charged electrons. That means there's 1 more positive charge than there is negative charges. So when sodium loses that outermost electron, it becomes an ion. It's no longer an element, it's an ion. And you can easily identify ions in the written form, everybody, because when you see the element sodium written out on paper, it's just the letters Na. And then right above it in superscript, you'll see a plus sign. That means +1, because there's 1 more positive charge in the nucleus than there is electrons going around it. So it has a net +1 charge. Chlorine is element number 17. It fills out the first 2 orbits just fine. There's 2 and then there's 8, but the outermost orbit has 7 electrons in it. It's capable of holding 18, but there's only 7 there. Now here's where I'm going to gloss over, everybody. In the world of chemistry, an element will become stable if it can satisfy 2n² in the outermost orbit. If it can't do that, then it will be stable if that outermost orbit possesses either 8 or 18 electrons. And I'm not going to explain to you the significance of the numbers 8 or 18. That's what I was talking about glossing over earlier, everybody. Just know that it's the numbers 8 and 18. If it can't satisfy 2n², it will settle for either 8 or 18. And there's a reason for it, but I'm not going to explain it to you. Chlorine has 7 in its outermost orbit. If it gained 1 more, it would have 8. Sodium wants to give up 1. So sodium and chlorine are going to be naturally attracted to each other. One of them wants to give it up. One of them wants to receive it. And then you end up with NaCl, or common table salt. Water works the same way, everybody. Hydrogen is element number 1. Hydrogen has not satisfied 2n squared in the first orbit. There's only 1 electron there. Oxygen is element number 8. That means there's 6 electrons in the outermost orbit. That's orbit number 2 in the case of oxygen. There's 6 electrons there. It wants to have 8. So that means it's got to find 2 electrons. Where's it going to find them? Well, 2 hydrogen atoms are going to come along and give up each of them give up their 1 electron to that oxygen, and boom, you got H2O. So when you look at the diagrams, everybody, that's kind of how that works. It's magnetism that attracts elements to each other. One of them is negatively charged, one of them is positively charged. Only opposites mix. You can't take a positive element with another positive element and get something out of it. It's not going to happen. It's like trying to push those 2 magnets together, but they have a natural tendency to want to push away from each other. So no, you can't mix sodium and potassium, but you can mix either potassium or sodium with oxygen because it's a negative. So that's how the various elements and minerals come to be within this earth, everybody. Okay. Once again, the only thing I need you to know is the number of protons in the nucleus identify the element, and the electron configuration determines the chemical and physical properties of that element. And that means what color is it, how heavy is it, what's its boiling point, what's its freezing point, how easily does it mix with other elements. These are characteristics, okay? So those are the only 2 things I need you to know for exam 3, okay? The other diagram that's in one of the handouts is the structure of the Earth. It's the layers, everybody, the layers. Earth has many layers. I'm not going to ask you any questions about mileage, you know, how thick is this layer or that layer. But we know quite a bit about the interior of the Earth, even though we've never been there. Any wild ideas about how it is we find out about the interior of the Earth? Anybody, any clue as to how we do that?
My guess is the distance from the North Pole to the South Pole, and then from the side of the world to the other side, and then you kind of calculate that to the middle.
Well, you're talking about physical dimensions. I'm talking about the actual physical makeup, the chemical properties of the interior of the Earth. In other words, what do the layers look like? It's actually quite simple. The technology has been around for quite a while. It's just not been applied in this fashion until the last 50 years. We basically take sonograms of the Earth. We do it to expectant mothers all the time. And out of those sonograms, you get to see Junior in all his glory. You can make out the gender, you can make out the arms and the legs, the toes, and you know, once you're in the 3rd trimester, heck, you can make out the nose, the mouth, the eyes, the ears. Well, we do the same thing with the Earth. The trouble is we need a little bit more power than comes with the normal sonogram machine that we do on Mom. So one of the ways that we send sound waves completely through the Earth, and you got to remember, when you do this, you have to make precise timing measurements. So the reason we've only been able to discover the interior of the Earth, what it is made up of and how thick the various layers are and whatnot, we've only been discovering this for the last 50 years or so. And the reason has to do with technology, obviously, and precise timing. And here's what I mean by that. We've throughout the entire history of humanity, there's been recorded earthquakes throughout human history. So by the time you get to the 19th century, mankind had earthquake monitoring stations all over the globe. So what would happen is they would be able to pinpoint the epicenter, you might say, based on triangulation, because when the earthquake occurs, it's going to send out a shock wave. And so how quickly does that shock wave reach, let's say, for instance, the California coastline? And how quickly does it reach Alaska? How quickly does it reach the Hawaiian Islands? And you have to have precise timing, and that will tell you where the epicenter is, okay? And in the 19th century, the technology wasn't near as accurate as it is today. So their ability to measure the timing of these shock waves sometimes was not very accurate. Well, then along comes World War II, and we invent the atomic bomb. The nice thing about the bomb, everybody, is, if there is such a nice thing, you can call the entire world up on the phone, because it's required by international law that you do this. Every time you test a nuclear weapon, you have to let the world know that you are about to do this, because everybody's earthquake machines are going to register it as an earthquake. The nice thing about nuclear weapons used in this fashion is that the timing can be precisely honed, because you can set a bomb off in the state of Nevada, and you can call up the world and tell them at precisely 7:30 Pacific Standard Time, we will generate a shock wave. Please take measurements. And so after decades of doing this, we've built up a pretty accurate picture of the layers of the inside of the Earth by performing basically these. Every time we did a nuclear test, we were sending a shock wave through the Earth. And depending on how much time it takes the shock wave to go through the Earth, it can tell you everything from what the rock is made up of, how dense it is, how thick it is. So we have a pretty accurate picture, even though we've never been there. We have a pretty accurate picture of what the interior of the Earth looks like. And so in one of the diagrams that I gave you, it's all the various layers of the Earth. And I'm more interested in you knowing some of the characteristics of these layers than I am mileage or how many kilometers thick is this thing. That's not what I'm interested in. I'm more interested in that you understand what some of the characteristics are. So the core of the Earth on the diagram, I'm going to work my way from the center out towards the surface. The core of the Earth is made up predominantly of iron. There's other trace elements in there, but it's predominantly iron. The temperatures at the center of the Earth are hot enough to completely liquefy iron. However, as you know, at least I think you know, you cannot compress liquid. Many of you found this out the hard way as kids when you jumped off the high dive at the public swimming pool and you did that world-class belly flop on the water. You found out the hard way You cannot compress a liquid. So the weight of the earth is pushing down on the core. And even though the temperatures are hot enough to liquefy the iron, it's behaving like a solid. And it has to do with all of the pressure and the weight of the earth on top of this core. In other words, there's no room for the liquid iron to slosh around. It's just literally contained by all the pressure of the earth on top of it. The outer core, on the other hand, is not under as much pressure as the inner core. So the outer core does, in fact, rotate. It's kind of in a quasi-plastic state. It's hot enough to liquefy, yet it's still under a tremendous amount of pressure. So it's not quite acting like a solid either. So it does rotate. And it is the source of Earth's magnetic field. Earth's magnetic field is generated in the outer core. One of the ways Earth's outer core basically makes planet Earth a rather large magnet, if you think about it. I don't know how many of you are aware of this, but maybe you did this in middle school during shop class, or maybe you just did this playing around the house. If you take an ordinary magnet and then you take an ordinary iron nail and you rub it across the magnet, you will magnetize the nail. Okay, get it? You're taking an ordinary nail, rubbing it over a magnet. That's all you're doing. You will magnetize the nail. What do you think happens to all of these big, huge metal ships driving over the world's oceans for, say, 8 or 10 years? Do you suppose that sounds a little bit like rubbing a nail over a magnet? That means the hull of these ships becomes magnetized. And that's dangerous, everybody, because what'll happen is the computer electronics on board the ship will start thinking that the bow of your ship is north. So as you can imagine, no matter what direction you turn, you will always be pointing north because the electronics on your boat think the bow is north, not real magnetic north. So about every 6 to 8 years, even those big, huge aircraft carriers and those big, huge oil tankers, they have to come up out of the water. And they have to be demagnetized. It really messes with all the electronics on the boat if you don't do that. So Earth is basically a big, huge magnet. And it's the layer that is responsible is the outer core. The largest of these layers is the mantle. It's pretty much rock all the way through, and it's mostly made up of granite. And then immediately above the mantle is a small layer that I have labeled. It's pronounced asthenosphere. It's the uppermost layer of the mantle. And it exists also in a somewhat quasi-plastic state. It's not completely liquid, yet it's not completely solid. This is what the crust sits on top of. You are standing on the crust, and it is sitting on top of the asthenosphere, which is not completely liquid, yet It's not completely solid. So it's acting like grease under the wheels, and it's partially responsible for allowing the continents on this planet to move. The crust is the outermost layer, and it's cracked. I already went over this yesterday. Some of these cracks you're familiar with. The San Andreas Fault is one of them. It's the thinnest of all the layers. It varies in thickness between 5 and 40 kilometers. It's thickest on top of dry land. So the thickest portion of our crust is on top of the Tibetan Plateau in southern China. The thinnest portion is located at the bottoms of the oceans. The deepest point in any of our oceans, everybody, is in the Western Pacific near the Marianas Islands. The deepest point in any ocean is 39,000 feet. That's deep. And for those of you Leonardo DiCaprio fans, I'm sorry, but that's 3 times deeper than the Titanic is currently sitting at. So the Pacific Ocean is pretty deep. And to give you some idea of how technically challenging pressure can be, because at 39,000 feet, everybody, you are under 1,200 atmospheres of pressure. Human physiology cannot tolerate that. It would squash you like a pancake. We've only sent 2 human beings down to the bottom of the Pacific Ocean. There's no pressure on the moon. We've sent 12 humans on the surface of the moon. That should tell you everything you know about how difficult it is to deal with the common problem of pressure. When there's no pressure, we deal with it a lot easier. When there's a lot of pressure, that's harder to overcome. And I think that point illustrates it nicely. Only 2 people at the bottom of the ocean, 12 people on the moon. So anyway, the crust is the smallest, it's the thinnest layer, it's the one you are standing on. It is fractured into pieces. There are 7 large continent-sized pieces, plus a dozen or more, maybe even 2 dozen smaller pieces that the Earth's crust is fractured into, okay? So don't worry, I'm not going to ask you to name these pieces. Common names would be the North American plate, the Pacific plate, the South American plate. See, you get the idea. But no, I'm not going to ask you to name plates, no. Just know that the crust is the smallest, the thinnest layer, and it is fractured, okay? Does anybody have any questions about anything up to now? Okay. As soon as this recording is available, I'll send it out to you, and otherwise I will see everybody tomorrow.
Thank you.
Recording stopped.
Bye-bye.